implemented paraphrase detection and semantic similarity for this project. So the problem statement here is that if you have two pairs of two sentences, how can you tell if they qualify as a paraphrase, i.e. if they contain the same information? And further, how can we measure how similar two sentences are in terms of semantics? So whenever there's a human input or an unstructured input of any kind, there is a use case for this, basically. If you have a chatbot, for example, one of the things you want to do is be able to tell if two questions, even if they contain different keywords, are asking the same information. That way you can refer to the same documents perhaps, or call different sub-agents depending, or something like that. It can also be used for recommendation systems and clustering purposes. So if you type in something, maybe the system could use item descriptions and paraphrases of that to match that to what you put in to give you recommendations for products. This is one example of where you can see it in action. Perplexity creates paraphrases of what the user typed in and uses that to search different sources. So the idea is that this paraphrase detection and semantic similarity sort of detection mechanism would be used as a prefetching or a first step in a system like this. So in terms of the frameworks and tools used, the Hugging Face Transformers library gives you access to the BERT family of models. And although one of the models was used for our foundation for this project, the Hugging Face ecosystem proved easy to use around it. So the way this was structured is I took BERT and then fine-tuned it on two different data sets. The first one was this standard benchmark data set called MRPC, and this contains a variety of different kinds of sentences, and it's explicitly labeled with whether it's a paraphrase or not. And this was used to train the classification head of BERT as a starting point. The second one was a more challenging data set. This explicitly is sort of designed to have sentences that have a high degree of lexical overlap. Things like swapping out individual words or changing the structure of the sentence where they contain almost the same information but not quite. And this really forces models to learn linguistic structure and nuance as opposed to just doing keyword matching, which tends to be a bit easier for models to do. So this is a sort of illustrative example where these sentences are the exact same, but there's a single word difference, hotels and homes. And these are, sort of in the same family of words. So it would be easy for a model to get this wrong if it were just doing keyword matching for things like named entities like Pine Street, for example. So these are the fine-tuning results. We can first look at how we got them in the notebook. So we start off up here by downloading the dataset and tokenizing it using the BERT inbuilt tokenizer. This was the example that we saw earlier, and I used the trainer API to train them. Initially, I had tried to use TensorFlow with Hugging Face, but the later releases of Hugging Face proved sort of incompatible with using TensorFlow. I don't think it's supported anymore, and as a result, it was just easier to use this trainer API and then use PyTorch later. Otherwise, it would require very sort of strict version control of what versions you were using of different libraries. So let's start off by seeing how accurate the fine-tuned model was on the test set for MRPC. And as we can see, it achieves a reasonably high accuracy and F1 score. If we go down here to the evaluation section and look at the loss over steps, this is sort of characteristic of a little bit of overfitting perhaps, since we see that the validation loss going up over time towards the end. So just to see how well this generalizes, let's just test this model out on pause, just straight out of the box, after fine-tuning on MRPC. So as we can see here, this is actually just on MRPC. These are pairs of sentences and the sort of predictions that we got and the probabilities. So for sentences that are paraphrased, it classifies them accurately for the most part, as you can see. But for non-paraphrased sentence pairs, where they're not the same, it gets it wrong more often. So it has low precision, since there's a higher rate of false positives. So let's look at a more adversarial dataset like pause first. Now we tokenize the pause dataset, which is more challenging, and if we go down here, we can see that running the same exercise, it struggles to classify these as zeros, which is what they should be. It says that they are paraphrases of each other when they're not. So it's difficult for it to grasp the sort of subtle differences between these pairs of sentences. As you can see here, the accuracy in F1 are quite low. Let's see if we can improve them by fine-tuning it on pause. So this is the sort of fine-tuning section. And this is indicative of potentially the fact that if this had been trained for longer, the accuracy could go down, it could go up even more. We see the training and validation losses going down over time, which means that if I had potentially trained this for a lot longer, this could have performed better. So we did get a bump in accuracy. I think the F1 score wasn't passed into the evaluation here, but it was a sort of modest bump in accuracy. Potentially training for longer would have improved this. So let's take this fine-tuned model that we just created and use it to implement Siamese encoders. So what exactly are these? So this is a different mechanism of paraphrase detection, where you actually are able to calculate the cosine similarity between two sentences. Now, what's the point of doing this, given that we just used BERT to sort of create a cross-encoder mechanism? Here, instead of encoding both sentences at the same time, you encode one sentence each independently. It's sort of like the twin Siamese metaphor, I guess they were using here in the title. So we use the fine-tuned model here. We use mean pooling to create a vector, and then we calculate the cosine similarity. So you can pre-calculate these encodings and then cache them potentially, and then use those to calculate the similarity between any two sentences. And so this could give you a big performance boost, because if you already have these loaded up, they could be matched with any other sentence. So let's see how we did this over here. So the main two concepts here are mean pooling and contrastive loss. So for mean pooling, the idea here is basically that you create a single sentence vector from tokens of the same size, irrespective of how long the sentence was. Now, contrastive loss, this is the sort of training mechanism that we'll be using here. If we go down, the idea is that we calculate the cosine similarity, and it creates a cosine similarity matrix where we are only using the positive examples here, i.e. where they are paraphrases. So what happens is that it creates a batch, and let's say you have a sentence and you have its pair. The pair is treated as the true match, and all of the other sentences in the batch are automatically treated as negative samples. So to train this, you don't need negative samples, which is a huge boon in terms of the kind of data that's out there. So after that, it uses this info NCE labeling objective function, and it treats the similarity task as a multi-class classification problem. And as we said, we don't need negative samples, and it pushes the true paraphrases closer together and pushes the negative samples that it's created in this cosine similarity matrix further apart. And so after sort of messing around and picking these hyperparameters, what we see here is that we can train this model again on the pause data set and then see how it performs on different sentences. So if we encode this and we have two different types, let's use this example, we see that these are not, they're sort of similar to each other in that they're talking about indexes, but they're different enough that they are not paraphrases of each other. So you see the similarity score here is high, but not 1. Now let's look at the pause data set, the harder one. So these sentences are almost the same, except for they're talking about different people, but it still gives it a high similarity score, which means that it is not grasping the small nuances quite as much yet. And if you look at the range for the different data sets that we get for similarity scores, here we get quite a range, which means that it's able to sort of distinguish between the different sentences and their meanings more on this data set because they're very different from each other. Whereas for pause, it still struggles to distinguish between the sentences that are almost the same, but ever so slightly different. So what can we sort of learn from this? So since, as we spoke about earlier, since negative samples are not needed for this network, we could adapt many question-answer data sets to further train this and to improve robustness. So these are two data sets that I'd initially tried to use, basically, but it was very difficult to create negative samples, i.e. sentences that are not the same. These are basically sets of questions that are all mapped to the same answer. So the questions are all paraphrases of each other. And so this could potentially help with, chatbot question answering. So this opens up a sort of window of possibility of even if you don't have negative samples, you could still train on these data sets. Second is, as we spoke before, this can be used more efficiently since you can cache encodings and reuse them instead of having to, for every single pair, generate a new encoding like just the fine-tuned BERT would have done. And lastly, a lot more training is required for models to grasp linguistic nuance. Keyword matching and general sort of family detection in terms of semantics is much easier, but to achieve the precision and recall for answering questions very specifically like we want, it requires a lot more training and potentially more specific training on data sets like these. Okay, thank you.